Hello everybody, it is Chemistry, University of Winnipeg, 1112. Dr. Carroll here with Weak Acids and Bases, Chapter 15, Lecture 2. We are on page 735. Most of this will be a review from last year, but last year was a long time ago, wasn't it? So, most acids and bases are weak. We looked last class at the strong acids, of which there's only 6, and the strong bases, of which there's maybe 8 common ones. Everything else is weak, which means you do not have much transfer, if we're talking about a weak acid, of the acidic proton to the receiving base. Typically, less than 10% is dissociating if we're talking about a weak acid. We're talking about weak bases, less than 10% ionizes. You can get cases where there's more, but in general, everyday laboratory conditions and processes, 10% or less is common. We're going to do an approximation most of the time to avoid using a quadratic equation, where we will assume that the amount of protons transferring from the acid to the base is negligible relative to what you start with. So that approximation works well as long as the initial concentration of the acid is greater than around 100 times the acid ionization constant. This book talks about as long as the percent ionization is less than 5%. There's some sort of borderlines on this, and we'll see these as we go through. So if we had hydrogen fluoride and thought it was a strong acid, let's hope that my pen's working today. Good. Yeah. You would think that the pH would be the negative log of 0.25, right? You'd think that all the H3O plus would come out of solution. So what would be released? So I would take the log of 0.012 and I would get 1.92. Now, the pH of a 0.25 molar solution is 1.92. What you would think if it was a strong acid is that the pH would be the log of 0.25, that all of it, invalid operation, okay, I've had those before, log of 0.25 would be 0.60. The fact that the pH of hydrogen fluoride or hydrofluoric acid is the way we talk, naming system we use, is not 0.6, but rather is 0.012, gives us a clue that, hey, HF is not a strong acid, it is a weak acid. Okay, not all of the 0.25 moles in a liter becomes a protonated water, right? The H of HF is not transferred as a proton over to the water to form H3O plus in a large amount. Here's the picture of it. Oh, they like to, I just write it like this. HF goes to H plus F minus. They want to be fancier and do HF plus H2O. First of all, this is wrong, isn't it? Why is there a 2 there? Just be H2O liquid plus HF goes to H3O plus F minus, right? That's balanced. Imagine that there was a typo. Oh my goodness. Okay, so my Ka, my acid ionization constant, or dissociation constant, is H plus times F minus over HF. So theoretically, the key concept is in a solution of a weak acid, only a small fraction of the protons are transferred to the base. Okay, so let's go on and do some examples here. Right into business. So we talked about the pH of a 0.25 molar solution is 1.92. Calculate the Ka. So here we do use our ice diagrams. My HF was 0.25. My pH is 1.92, so my H3O plus is 10 to the minus 1.92, or 1.2 by 10 to minus 2. So at equilibrium, my H3O plus is 1.2 by 10 to minus 2, and it's a 1-to-1 ratio with my F minus, so the anion is also 1.2 by 10 to the minus 2. I started with 0.25 of the HF. I lose 1.2 by 10 to the minus 2, so I end up with 0.24 if you care about sig figs at all. So then my Ka is 1.2 by 10 to the minus 2 squared over 0.24. Okay, there's no approximations in this. Here, this kind of question, we're given initial data and we're given equilibrium data. Not directly, we're given the pH, but from the pH we can get the H3O plus concentration, and then we can calculate Ka. So Ka is 6 by 10 to the minus 4. So this is a classic kind of question. Almost all weak acids that we'll look at will be monoproduct. There'll be a little diproduct and triproduct, but the vast majority of the ones we'll look at will be monoproduct. Okay, let's try this. Propanoic acid, calculate the Ka. So you have a whole bunch of stuff there. I just like to write it as H-prop. Okay, we don't really need to put in all that other stuff here to answer our questions. So it's H-prop positive plus the propanoic anion. So initial change equilibrium. So the propanoic acid, 85 millimoles, so that's 85 by 10 to the minus 3, or 0.085, right? 8.5 by 10 to the minus 2, and roughly 0 this and 0 this. And the change, we're going to lose this because this is an equilibrium system. It's going to go to equilibrium. And then at equilibrium, we're going to get some values. So Ka is H plus times PROP minus divided by H PROP. That's what we want to solve for. So they tell me the pH is 2.97. So that is my equilibrium value of H plus. It's not 2.97, it's 10 to the minus 2.97. That's right. Okay, so I've got to get this fancy calculator, cell phone thingy here until I find batteries for the other thing. Clear. So I'm going to do a second. 10 to the minus 2.97, I get 0.00107. Okay, 0.00107. So that's how much I gain. 0.00107, 0.00107. So at equilibrium, my H plus will be 0.00107. My prop minus will be 0.00107. 0.00107, and my H prop will be 0.085 minus 0.00107, which is 0.08393. 0.08393. Oh, I'm doing too many sig figs, aren't I? 0.00107 squared divided by 0.08393. 0.08393. 0.00107. 0.00107 times 0.00107 divided by 0.08393. 1.28 by 10 to the minus 5. Okay, let's check if that's right. Practice exercise 15.6. 15.6, 1.4 by 10 to the minus 5. 1.3 by 10 to the minus 5. Okay, so they're rounding their sig figs. Get it a bit different than what I got it, but it is close enough. Okay. The pHs of weak acids are still less than 7, right? Okay. Okay. Here's a nice picture on page 737 showing for a strong acid like HCl, when you dissolve the HCl, you get the same amount of cation and anion, essentially all of it. For HF, you dissolve the HF, maybe the same initial concentration as the HCl, and at equilibrium, you have hardly any of the H3O pluses and F minus. So you see the stark difference between strong acid and weak acid. Okay. The percent of HA that's hydrolyzed is 100 times how much of H3O plus you have at equilibrium over how much HA you started with. Percent ionization is another phrase you may have heard last year in your other readings. So in the example, and I was just going to go back and do it, but this book is doing it for us. In the hydrogen fluoride, the percent ionization is 100 times how much we lost of proton, how much was converted, which is how much H3O plus is at equilibrium, so 1.2 by 10 to minus 2 out of what we started with. So less than 5%, less than 5 out of 100 molecules actually hydrolyze. That means react with water. That means give the proton to the water. And since I did all that work, we might as well do the practice exercise there. So for this propanoic acid, the percent ionization or hydrolysis would be 100 times how much H3O plus at equilibrium, 0.00107 over what we started with, 0.085. So 0.00107, clear, 0.001, oops, clear, 0.00107 divided by 0.085 times, okay, times 100, 1.25, so 1.3%. Okay, so that's even small. Sometimes you have even less than 1% dissolving. You have less than 0.001% dissolving. So let's try this one together, still with hydrogen fluoride. Determine the percent hydrolysis for an aqueous solution that is 25 by 10 to the minus 3 molar. So we know the value of the equilibrium constant. It's 6 by 10 to the minus 4. Oh, okay, we're going to do everything with this. So we know that from previous. So this type of question, you know Ka, and you know initial concentration. You got to get equilibrium concentrations and percent hydrolysis. So here's how it goes. We start with 0.025 of the HF, 0 of the others. Let's let X be how much of the HF reacts. So we lose X of that, gain X of the H3O plus, and X of the F minus. So at equilibrium, I got 0.025 minus X of the HF, X of the H3O plus, and X of the F minus. So my Ka is X times X, X squared over 0.025 minus X equals 6 by 10 to the minus 4. That was given. So this question is different than the one we had before. This one you are given Ka. Now, we have an initial value 0.025 for the HF, and the Ka is 6 by 10 to minus 4. The way I've seen in other books, whether we have to do the quadratic or not, if I take 0.025 divided by 0.0006, I get 42. That is right on the borderline whether I can avoid the quadratic or not. Typically, if your initial concentration is greater than 100 times Ka, the approximation works. Well, this one it's only 41 times, so the approximation won't work. So you have to do a quadratic equation. It's not scary. I'm not going to do it because I see it all written here, and you are all capable of doing quadratic equations. I mean, most of you are taking the university calculus course. So the approximation would be I'd get rid of the x in the denominator, and then I wouldn't have to do a quadratic. But here I multiply both sides, plug them into my roots equation. X is minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. And I get two roots. One of the roots would give me a negative value for HF. So that wouldn't be physically valid. I mean, it worked for the math, but it doesn't make any sense in terms of the physical conditions of the question. But the other one does, 3.6 by 10 to the minus 3. And so that gives me my X. And so then my percent hydrolysis is 100 times 3.6 by 10 to the minus 3 divided by 0.025. So 14% hydrolyzed. So that's a big percentage in the world of weak acid stuff. My F minus would also be 3.6 by 10 to the minus 3, and my HF would be 0.025 minus 3.6 by 10 to the minus 3. And then you could check and see you get Ka. A common pitfall is making the simplifying assumption when it's not actually allowed here. If you aren't sure, use the quadratic equation, which will always give you the correct result. So let's try this example here. HF, did we just look at HF? That was HF, right? Yeah, so let's look at it again. But instead of starting with 0.025 molar, we start with 1 molar. Okay, so if I go, let me try to do it over here in the margin here. If I have 1 molar, so I'm going to get the Ka 6 by 10 to minus 4 is x squared over 1 minus x. Now here my initial amount is definitely a lot more than 100 times, so I can make the approximation. The approximation is that the x in the denominator is negligible. It means it can be ignored relative to the original concentration of the acid. So then I cross multiply, so I get x squared is 6 by 10 to the minus 4, so x is the square root of that. Yeah, this is a lot easier, isn't it? Ooh, square root, don't know how to do that on this fancy cell phone, Apple, iPod, Nano thing. So let's see, do I have a square root? I gotta have a square root somewhere. I can just raise to the, oh no, there it is. Square root of 6 by 10 to the negative 4 is 2.45 by 10 to minus 2. Okay, I could get the pH if I wanted to. It didn't ask for that, but I could get, what does it ask for? Determine the percent hydrolysis. So it's going to be 100 times x, 2.45 by 10 to the minus 2 over how much I started with, which is 1. So it's 2.45%, which is less than 5%, which works within the testing scheme of this particular textbook, so that's good. Again, I could get the pHs and the pOHs of those two. And for more practice, you can try those problems 15, 2.3, 2.4, 2.7, and 2.8. Okay. Weak bases. Well, it's, again, I said this earlier, it's usually derivatives of ammonia that are used. So here's ammonia. You have it accept a proton, Bronsted Lowry base, proton acceptor, so you get NH4 plus and OH minus. So my Kb, you don't call it, the base doesn't dissociate, it doesn't break apart. It causes the water to break apart, really, and ions are created. So you talk about percent ionization in the process is Kb, or the base ionization constant. So it's my NH4 plus at equilibrium times the hydroxide over my NH3. And that is my Kb. And in a solution of weak base, only a small fraction of the protons are transferred from the acid, not to the acid, but from the acid. Okay, so ammonia has Kb is 1.8 by 10 to the minus 5. We're going to hear this 1.8 by 10 to the minus 5 a lot because it's also the Ka for acetic acid, which we use a lot in examples. Ka of acetic acid to 1 decimal is 1.8 by 10 to the minus 5. So it's just a coincidence that the Kb of ammonia is the same number to 1 decimal as the Ka of acetic acid. So we want to get the pH of 0.25 molar ammonia. The book does this other stuff with putting the water in, which is just annoying and doesn't help at all in 99% of the questions. So I'm not going to bother with it. On a test, you wouldn't deal with that. You'll just look at, here I think we'll be able to use the approximation because I see equilibrium constant, and yeah, that's more than 100 times less. So hooray, I'm not going to have to do a quadratic here. We want to get the pH and all this other stuff. So here we go. Initially, we had 0.25, so we're given that, and we're also given Kb. Is that true? Did initially we start with 0.25 molar of the aqueous ammonia? Yeah, we did. Okay, so those are the two things we're given. We got to find everything else. So the NH4 plus and the OH minus are both 0. In the next chapter, chapter 16, we'll see where some of these aren't 0 originally, and we'll talk about something known as a buffer solution, which is interesting. Okay, so then we're going to lose X of the NH3, gain X of the NH4 plus, gain X of the OH minus. So at equilibrium, I'll have 0.25 minus X of the ammonia, X of the NH4 plus, and X of the OH minus. So my Kb is going to be X times X squared over 0.25 minus X is 1.8 by 10 to the minus 5. Because my initial is at least 100 times here, I can get rid of the X. In the denominator, cross multiply, take the square root, and I get OH minus is 2.1 by 10 to the minus 3, which means the POH is 2.68, and the pH is 14 minus that, which is 11.32. My H plus concentration will be 10 to the minus 11.32. To the minus 11.32, which is 4.79 by 10 to the minus 12. So that's my H plus concentration. So I got my pH, POH, OH minus, NH4 plus, H plus, my percent ionization, percent 100, times how much X is. X is what? 2.1 by 10 to the minus 3 over what I started with, 0.25. So 2.1 by 10 to the minus 3 times 1 by 10 to the minus 2 is 2.1 by 10 to the minus 1. So it's just 0.21 out of 0.25, which is 0.84%. So less than 1% ionizes. Okay. And 15.8, you can try that one on your own. 85 millimeters. 85, not millimeters, 85 millimolar. So that's 85 by 10 to the minus 3. So 0.085. Yeah, that one should still work without doing, well, let's see. 85, what was this one? 0.25. And this one is, oh, let's just do it. 85 by 10 to the minus 3 is divided by 10, multiplied by 10, 8.5 by 10 to the minus 2, or 0.085, which is 0.085 divided by 0.000018. Yeah, that, the approximation should work for that. So that would be X squared, no, okay, 0.085 is the initial value. Good. So my Ka is not important. My Kb, 1.8 by 10 to the minus 5 is X squared over 0.085 minus X, and I don't worry about the X in the denominator. So X is 0.085 times 1.8 by 10 to the negative 5. Take a value and then take the square root of that value. They get 1.24 by 10 to the minus 3. So the pH is the log of that value times negative 1. So 2.91, and that's not the pH, that's the pOH. Oops, pOH. So the pH is 14 minus that. 14 minus 2.91 is 11.09. So I assume the approximation was valid here. Let's take a look. Practice exercise 15.8. 11.09. Hooray. Okay. So we see if we have a strong base, like 0.25 molar sodium hydroxide at equilibrium, we have no NaOH. You got the same amount of hydroxide and Na+. That the weak base, hardly any of it breaks apart, 0.25 molar NH3, you see that the pH is a lot less, which means there's not as much hydroxide in there. Okay? Okay, you can read some other fun, exciting things. 15.3.1. I'm going to let you do that one on your own. I don't. Well, I wonder if you have to use the quadratic equation or not. You know what? You're gonna try that on your own. Okay. Let's push a little bit here. 15.4. Recognizing acids and bases. We have some pictures here of from that review, the beginning of this chapter, the high school review. I mentioned oxoacids. They're sometimes called oxyacids, and you're going to have a nonmetal like nitrogen here with oxygens doing their best to surround them, and then acidic hydrogens dangling from an oxygen. Okay, so here's a snapshot example of one of the Lewis structures contributing to nitric acid, so HNO3. So the hydrogen is not directly bonded to the nitrogen, it's bonded to the oxygens. So when you hear the word oxoacid or oxyacid, think of oxygens trying to surround the other nonmetal and hydrogens dangling from the oxygens, as we see in carbonic acid. Phosphoric acid, you have 4 oxygens around the other nonmetal, which is phosphorus, and the hydrogens are special. They dangle from the oxygens. Sulfuric acid, we see the oxygens around the sulfur. And why are there 3 hydrogens there? That does not look right, does it? Huh. Let's just chop that guy off, right? There you go. Chlorous acid, HClO2. Chlorine, oxygen, and then a hydrogen. Okay, so that is some examples. Most of them are weak. Nitric acid isn't, but the other ones are all weak. Sulfuric acid is controversial. The first proton being released does so 100%, but additional ones do so less. So oxoacids contain an inner atom bonded to a variable number of oxygens and acidic OH groups. Really? I don't know. I would just say the hydrogens are bonded, and hydrogens are bonded to the oxygen. That's better. So here's some names: chlorous acid, nitrous, hypochlorous, hypoiodous, iodic, and there's Ka values. As you remember from equilibrium constants, the larger the value of Ka, the stronger the acid. So even if the acids are weak, you can still sort them, just like in the NHL. Not all teams make the playoffs, but the weaker teams can still be sorted, even though they aren't strong. There's still some teams which aren't quite as weak as others, and the Jets are at the bottom of the barrel, right? Well, maybe not. Maybe at the time that you're listening to this, the Jets just won the Stanley Cup. Okay, so we see here that the hypoiodous acid, HIO, is the weakest of the 4. Okay, and then you got the conjugate bases here. One thing we're going to get to more in the next chapter is the Ka times the Kb of the conjugate base is going to equal to Kw. So that's a useful thing for next chapter. Ka times Kb of the conjugate base equals Kw. Then there's some naming rules. Oxoacid, forming from a polyatomic anion, has name ending in ATE, or with a name ending in ATA becomes IC. So nitric acid came from the nitrate, so that's why it's called nitric. HClO4 is perchloric acid from the perchlorate. If the polyatomic anion ended with the ite, then the name of the acid ends with OUS. So HNO2 is formed by adding a proton to the nitrite, so it's called nitrous. Hypochlorite becomes hypochlorous. Hypoiodite becomes hypoiodis. Okay, it's just all this Latin stuff, all this naming stuff, and if you want to argue about all these, I mentioned this in class a while ago, you can join. I don't know how much it costs. I think $200 a year. The International Union of Pure and Applied Chemists. I have never joined, but I have gotten information to join about it, and I've just recycled that information. But for some people, it's very important to be on the forefront of controversial name changes, so they join this union and they vote and they debate, and good for them, right? Okay, so that's oxyacids. Carboxylic acids are the world of organic chemistry. You have a COOH group, and then R just means everything else. So I already mentioned these before. We looked at some formic acid, the simplest one. So you got H, here's a hydrogen, COOH. So the COOH group is my carboxylic acid group, then everything else is the remainder of the molecule. Here's acetic acid, which we use a lot. So there's my hydrogen, oxygen, carbon, 3 hydrogens. I bet some of you can use molecular modeling programs and make a nice ball and stick model of acetic acid. So in this organic acid, and I should say off to the sides here, all organic acids are weak acids. Okay, they're all weak acid. But to some extent, you'll get a chopping of the bond here, and the proton from acetic acid will run away. Here's benzoic acid. You got this benzene ring with a carboxylic acid group, and there you get the break, and you get the proton released in benzoic acid. Okay, so here we see acetic acid tossing a proton over to H2O, so you get the acetate and H3O+. Okay, so it's RCO2H. And so you get the ic ending again from the 8. So formic acid is stronger than acetic acid, which is stronger than did that the other way. Let's see. Formic acid is stronger than benzoic acid, which is stronger than acetic acid. They're all weak, but if we had to sort them, formic acid would be the strongest of those weaks. Then there's some other acids which don't fall into the categories above, like HCl, HBr, and HI. I mean, I can call them mineral acids, or they are examples of binary acids. There are only 2 different kinds. But the book just wants to summarize them here, and there's some hodgepodge catch-all ending here. Hydrofluoric, hydrozoic, hydrogen sulfide, hydrocyanic, and hydrogen peroxide. So those are all Kas, and the strongest of those is hydrofluoric. Yeah, they are listed in order strongest to weakest of those 5 Lewis structures, highlighting the acidic hydrogen. And something like H2S, well, they're both acidic, so you lose one proton and then you lose another. And that's a topic. Polyprotic acids, which we'll talk about in a future screencast in this unit when we talk about section 15.7. So we got this first one here, which looks like a substituted acetic acids. So this will be a weak acid. The second one here looks like an alcohol, doesn't it? So there's no reason to believe that would be a strong acid. So I'll go with weak acid. HCN, we just looked at that. That's a weak acid. HClO4, that's a strong acid. Okay. B says, it's not part of a carboxyl group. This compound is an alcohol, not a carboxylic acid. But we could argue about that. When we talk about this in class, let's do a bit of Googling, because I think we can still talk about that as being an acid. Even though, yes, it is classified in organic chemistry as an alcohol, I think to some extent you could still get that proton transfer. So we'll talk about that together. I don't want to pause and start mucking around now with that one. HCN, we know that that's a weak acid, and HClO4 is a strong acid. Okay. HF is a weak acid. Formic acid is weak. There's an ether. Now this one I can say for sure is not going to be an acid, because ether, you have CH3 and another CH3 bonded to an oxygen, so you don't have any hydrogens bonded to oxygen, so that won't be an acid. H2CO3, that's an example of a weak acid. Weak bases, we've already talked about those. The fact that many weak bases are derivatives of ammonia. So in other words, you replace a hydrogen with some other group, usually has a carbon on it, but it could be other things, and you can replace 1, 2, or even 3 of them. They're all weak bases, which means they aren't that strong base accepts a proton or releases OH minus. Weak bases, yeah, they accept a proton. All amines are weak bases. They don't protonate to an appreciable extent. So here's some: methylamine, dimethylamine, trimethylamine, right? So there's 3 methyl groups there. And there is, in lots of these, some biological chemistry associated with these. Pyridine, aniline, hydrazine, that's rocket fuel, that's quite reactive. Hydroxylamine. So these are all examples of weak bases. And here's some other ones. Aniline, I've thrown in there, and the Kb. So the stronger the Kb, the more it would want to actually get a proton. Methanamine or methylamine is used in, I think it's used in some lifestyle bad choice productions of things. I don't need to go into that anymore, do I? Dimethylamine, etc. Hydrazine is used in rocket fuel. Hydrazine is interesting. It's also used to clean the boiler tubes. You know, that scaling, like, because I never cleaned the humidifier, you get all the scaling of calcium. It's actually called scum. So in a big plant, which needs water for coolant and all sorts of things, after a while you get this inner coating of the pipes with the scum, so you throw hydrazine in and it cleans up the pipes. Here we have some amino acids, which are complicated, right? They both have acidic group and basic group and all sorts of things. Lysine and aspartic acids are 2 amino acids found in proteins. So you see here, you got an amine group, and you got a carboxylic acid group, and you got another amine group, you got an amine group, a carboxylic acid group, and a carboxylic acid group. So functional groups depends what they react with. So amino acids can behave as acids or as bases depending on what they react with. And then there's some other weirder things too. Okay, and some of these have been used in painkillers, as we see here. Morphine is listed, diazepam, all sorts of other amines and derivatives of them, and then you can try those ones on yourself. Okay, so acidic and basic salts will be the next topic, but now I am curious, so let's try to be a bit daring here and write, is an alcohol an acid? Oh, Bing, okay. Well, alcohol, okay. Is alcohol a weak acid? People ask. Alcohol is a weak acid. It is even weaker when compared to water. Hence, alcohols are acidic in nature. Well, someone said it to be so. In chemistry, alcohol is an organic compound that carries at least one hydrogen group. Okay, so, yeah, it can be thought of as a weak acid. Okay, that's good for now.